Good afternoon, everyone. I want to thank everyone for coming today, and I would like especially to thank Professor Vitor M. Zavala for being with us today. Vitor is going to present the seminar entitled Exploiting Physical Knowledge in Machine Learning as part of our large Gimscop control seminars. Vitor M. Zavala is the Baldovin da Pra Professor in the Department of Chemical and Biological Engineering at the University of Wisconsin-Madison, and he is also affiliated with the Mathematics and Computer Science Division at Argonne National Laboratory. He holds a Bachelor of Science degree from Universidade Ibero-Americana and a PhD degree from Carnegie Mellon University, both in chemical engineering. He is a recipient of NSF and DOE Early Career Awards and also of the Presidential Early Career Award for Scientists and Engineers. He was recently named a senior member of the National Academy of Inventors, and his research interests include data science, control and optimization, and applications to energy and environmental systems. As we have here many students, it is also interesting to let you know that he maintains a very active LinkedIn page, which has more than 25,000 followers. And there he discusses topics related to PSE and academic life, among others. So Vitor, thank you very much. I will pass the word to you, and so that you can start your presentation.
Excellent. Yeah, thank you very much. Thank you, Mauricio, for arranging this virtual seminar. I really appreciate it. It's always a great pleasure to connect with the Brazilian community, which is very close to my heart for a variety of reasons. So today I want to talk to you a little bit about some experiences we have had in our research on how can we leverage physical knowledge in machine learning. So I'll give you some examples through that. Before getting started, I normally just like to introduce myself. So as Mauricio mentioned, so I'm originally from Mexico. So I obtained my undergraduate degree in chemical engineering in Mexico City in a small Jesuit school that actually Ignacio Grossman, that probably you also know, attended at the same university a few years before me. Then after that, I moved to Carnegie Mellon to work with Larry Bigler. The topic of my PhD was model predictive control applied to polymerization reactors together with ExxonMobil. After that, I did a postdoc at Argonne National Lab. For those that are not familiar, the Department of Energy in the United States has a network of national labs. Argonne was the first national lab. It was founded by Enrico Fermi back in the 1950s. And it has a long history in nuclear engineering research and also computation. So it have a long history in computation. So I was very happy there at Argonne. So I decided to stay there for 7 years total. And then Jim Rawlings at some point, so you might recognize that name, when he was at Madison, he reached out and he said, you know what, you might want to become a professor. Would you be interested in going to Madison? And I said, okay, why not, right? So I decided to transition to academia in 2015, so 11 years ago. I still work with the national labs. So some facts about me: I'm married, I have a couple of kids. So here what you're seeing here is their daily intake of ice cream. So here in Wisconsin, we eat a lot of ice cream. So you can see that over here. And my favorite movie is The Big Lebowski. For those that might be familiar, it's a great movie. So I invite you to watch it. And I also like heavy metal and other things to do, right? Also, I wanted to tell you a little bit about the department. So here at UW-Madison, we have a long history, as you know, in many different topics, including transport phenomena, but also process systems engineering. So, but we also have new phases, and I want to introduce you to some phases. In the context of process systems engineering, we're very fortunate to have Styliani Avramidou, an assistant professor that works in the process systems engineering field, applied particularly with scheduling and circularity. Joe Paulson recently joined the department as an associate professor. This guy is amazing, has a lot of expertise in Bayesian optimization, physics-informed machine learning, topics related to what we're going to cover today, and also some other phases in other areas that we also work on. So if you're interested in learning more about the program, feel free to just visit our website and you might find some of the things that we're working on nowadays. For those that are not familiar with where Wisconsin is, so I was had no idea when I was in Mexico. So we're actually here close to the two big lakes, Lake Michigan, and this is Lake Superior. So this landscape makes it very beautiful. There's a lot of lakes. There used to be a big glacier 10,000 years ago that melted, and it created all this very complicated network of lakes. The University of Wisconsin-Madison is located here in the south of the state. We're very close to Chicago, so it's quite easy to access. So you fly to Chicago and it's very convenient to get in. This is an aerial picture of Madison. So as I was saying, there are lakes everywhere. So we're in an isthmus. So these are two different lakes, and the university is right next here to the lake, right? So obviously, I'm just showing you pictures of summer. During winter, it gets really cold. The lakes freeze completely. So, but that also opens a lot of cool activities. So you can do ice fishing, you can do skating, like ice skating and things like that. So if anyone would like to come visit, more than happy to welcome you. We receive visitors from all over the world, Latin America, all over the world. And so happy to just send me a message. I'm happy to host you here. All right, so let's talk a little bit about the topics of interest today. So I want to start with how do we encode physical information in data, first of all. Then we're going to talk a little bit about uncertainty quantification, because I feel that the way to think about physics is a way to incorporate information, right? So, and if you incorporate information, you reduce uncertainty. But then you need to have tools that allow you to kind of quantify that information gain. So we're going to talk a little bit about that. Then I'm going to give you some examples on how you encode physics in machine learning models, particularly in the context of Bayesian optimization. And then I'm going to close with this interesting discussion on thinking about physical spaces and thinking about these latent spaces that maybe do not have a physical kind of origin, and how do we kind of think about and reconcile those two alternative ways of thinking. And I think there are some interesting things that we can learn from there. So the fundamental question we want to answer in this talk is, how can we leverage physical information in machine learning models and workflows? Physical information appears in many different forms, so it's not an easy question, right? So it can appear in the form of equations, it can inform in terms of biases that we might have in our data and things like that, right? So just to give you some examples, so imagine that you want to build a neural network model and you want to predict if a molecule, for example, is going to be toxic or not toxic, or if it's high viscous, low viscous. So how do you encode that physical information? So the questions here is, can we predict properties of molecules directly from the molecular structure? And if we have some physical information about these molecules, how do we encode this, right? So typically you can encode this in the form of the data representation that you feed to the neural network. And I'll show you an example a little bit later that this is where the domain-specific knowledge of chemical engineers becomes very important. And it's not trivial to decide what information you're going to be feeding into the machine learning model. Another classical example that we see in applications is the fact that many of these physical models that we have available to understand complex systems, typically they are incomplete, right? So typically you can capture some aspects, but not all the aspects about your system. So a tangible example is this collaboration I have with Professor Ophelia Venturelli. So she has a background in controls and dynamics, but she applies that to biological systems. And one of the interesting applications she has is through experiments, they try to learn the interactions that you see in bacteria, particularly in the gut, in the human gut, right? So our human gut has thousands of bacterial species. These species are competing for resources, but they also collaborate. So they form this consortium. Obviously, you cannot observe this interaction, so you have to learn them from data, and that's part of the things that we're trying to do. So the question here is, how do we fuse physical models that we might have available to capture these interactions, and how we use machine learning to complement that physical understanding? Another application that is also typical in chemical engineering is we need to select chemicals, we need to select solvents. For example, in the context of what I'm showing you here is, can you select solvents that can extract targeted products from biomass, right? Typically, the library of solvents that we have available is in the thousands, right? So it's not possible to kind of screen every single thing. And also you might have many different products that you might want to extract, right? So the idea here is that you wanna, by doing some iterative kind of experiments, you want to have some form of intelligent oracle that recommends what new solvents to try. You collect your data, try to measure performance, right? Now the problem is that if you build this oracle just based on data, let's say using a machine learning model, this oracle might propose solvents that are maybe not physically realizable. So this is where maybe you can use tools of thermodynamics to tell you what type of solvents might be more thermodynamically favorable, and with this narrow down the space, and then use machine learning model to kind of search for solvents over that reduced space. So maybe that's another idea. I'm going to show you some results on that space a little bit later. This is another typical type of setting in chemical engineering, right? So typically in chemical processes, we have unit operations that we know very well, so we can model with your favorite process simulation package, right? And we understand thermodynamics, we understand kinetics, we understand many different things, right? So many units can be modeled well, but maybe from time to time, we're going to encounter new units. So for example, here I'm showing you a bioreactor, which is difficult to model from first principles. So this is where you can combine a physical model that maybe captures the physics of all the units, and then a machine learning model for those things that you cannot properly model from physics. So that's another way to kind of mix this type of thing. A little bit later, I'm going to show you as well this interesting idea of how do you deal with process design tasks where the challenge is that you have mixed integer variables. And I'm going to show you a little bit later about how can we encode these mixed integer variables using some of these machine learning models, and how you can use that to kind of accelerate some of the design calculations that we have available. All right, the last application I want to show you is the following. Typically, when we are designing a controller, let's say a model predictive controller, right? This model predictive controller is subject to a lot of parameters that you can tune. For example, you can tune the prediction horizon of your controller. You can tune penalties to different variables that you might want to penalize, right? Like soft constraints and things like that. And you can also tune constraints to make the controller a little bit more flexible or more strict, right? More rigid and things like that, right? So the big question is, how do you tune those parameters, right? So I'm going to show you a little bit later how we use these tools of Bayesian optimization for doing this tuning. And I'm going to show you how you can exploit physical information in clever ways to try to accelerate that search, so that you're not just following data, but you're also using some structural physical information about your system. This is motivates a little bit why you want to use physics in this tuning process. This is a simulation of this model predictive controller for an energy plant that produces cooling water and hot water. So what you're seeing here is the forecast of the electricity load, cooling water load, and hot water load, right? So as you can tell, there's a lot of dynamics, there's a lot of uncertainty in your predictions, right? Here what I'm showing you are some representative variables in the optimizer that the MPC controller is optimizing for. So you see, again, a lot of variability and stochasticity, right? So building these simulations is very valuable because it helps you analyze how the controller behaves over a long time horizon, over many different disturbances. But the problem is that a single simulation, just a single pass over an entire year, takes 3 hours of computational time. The reason for that is that at every time step, you're solving a linear program. And we know that we can solve linear programs fast, but when you're solving 8,000 of them, right? So the time accumulates, so you requires a lot of computational time. So this is why you want to incorporate this physical information or prior information to try to reduce as much as possible the number of simulations that you need to run. And I'm going to show you how you do that a little bit later. All right. So now that I presented some motivating applications, so just to kind of set the stage, I want to talk about now how do you do this methodologically, right? How do you encode physics information in our models? So let's start with data representations. In my opinion, the number one way that chemical engineers contribute to machine learning is the data representation. We are the ones that understand what information needs to be fed to that model, right? A computer scientist is not going to have that context. And I'm sorry if there are computer scientists in the audience, but I assume they're not. But they're trained for other things, right? Chemical engineers are the ones that understand thermodynamics, that understand what thermodynamic properties we're trying to predict, what thermodynamic information we don't have available, right? A tangible example of this is predicting properties of molecules, right? So a molecule is a three-dimensional object. You have atoms, you have bonds, right? You can represent this in 2D in the form of an image, right? That's the way we learn organic chemistry. This two-dimensional representation captures the topology and the identity of these atoms, right? So it captures the basic features of the molecule, but you cannot pass this representation directly to a machine learning model. You can pass it as an image if you want, but it's not going to be a very efficient data representation, right? So as a result of that, people have been working very hard over the last years to come up with data representations for molecules. One of them is in the form of networks or graphs, where it's a very natural representation for a molecule because you have atoms are the nodes and the edges are the bonds, right? And then you can also encode information about the atoms and the node and the bonds into the structure of the graph, right? But there are many other representations. For example, smile strings is a very popular representation. The way to think about this is a language for chemistry, right? So it has an inductive bias. People call this in the sense that it has a well-structured language for expressing how a molecule looks like, right? Once you have the smile string, you need to map this into a mathematical representation. So typically you use something like a one-hot matrix encoding, right? So it's just zeros and ones that capture the topology of this. Now, if you talk to people in the molecular simulation space, they will tell you, you know what? Don't use smile strings. All that you need to make a prediction for a molecule is what they call the sigma profile. A sigma profile is a summary of the electronic structure properties of the molecule. And it's a really powerful summary of what the molecule looks like, right? And it looks just like as a probability distribution. So this is basically telling you the probability of observing charges of different intensities at different locations. And you can feed this sigma profile to a neural network and it will do a very good job at predicting properties of that molecule, right? The challenge is that computing the sigma profile requires a DFT calculation, a density functional theory calculation. So as a result, it's very difficult to get that information. It's a little bit more challenging, right? Finally, the other way that we can represent molecules is by representing their basic physical properties, right? So maybe I can predict the property of a molecule based on density or viscosity or volatility, things like that, right? The reason why I like to show this slide is that you see that there are many representations, many ways of encoding the physical information, and it's not obvious what is the right way to go. But if you ask a domain expert, they will tell you, use whatever is more interpretable. Use whatever uses features that we can actually interpret once you make and construct your model, right? All right. The other way to encode physical information in machine learning is not only through the data representation, but it's simply augmenting the architecture to capture that information, right? So imagine that we start with a simple neural network, right? So I feed my inputs, I obtain my outputs, and I have a neural network architecture with some learnable parameters, right? So feed-forward neural networks are kind of the standard basic approach for doing this, right? You can also build models that instead of learning static data, they also model dynamics, right? So maybe this input is time dependent. So maybe I want to model the evolution of some variable as a function of this input. So in this case, the neural network is capturing more that dynamic evolution of the system, right? So this is what differential neural networks or neural differential equation models are actually doing. Another architecture that is used quite a bit in machine learning are autoencoder networks. This has become one of my most favorite architectures for doing machine learning. So the idea, and it's very interesting, is you start with an input data, X. You're going to train a machine learning model that is going to project this down to a latent space. So the latent space is this output Y. This latent space does not have physical interpretation necessarily. So it's an abstract entity, but potentially very informative, right? And this latent space is built in such a way that you can go back to the original space. So in some sense, you want to build this latent space in a way that is highly informative. This approach is very effective at projecting high dimensional data, like the ones you encounter in chemical plants, right, into low dimensional spaces, similar to PCA, right? Another very interesting anecdote about this architecture is that it was invented by a chemical engineer, a professor called Mark Kramer, that at the time was at MIT. This was back in the 90s. So I found that fascinating that chemical engineers actually invented this technology for doing autoencoders, and it's very, very interesting history there. All right, the last architecture that I wanted to mention is Gaussian processes. Gaussian processes compared to neural networks are non-parametric, right? So the parameters are not part of the model structure directly, but are part of the uncertainty representation of the model. So these are probabilistic models that operate very well when you have low dimensional data. So when you have like a few measurements, right? So maybe you have 50 measurements or 100 measurements, you don't have millions, right? So they tend to work very well in that low dimensional space. And also in the space where you have very few inputs, as opposed to a neural network that can operate with very high dimensional inputs. All right, so now how do we embed this information into the architectures that we have? The simplest approach is to do this, right? You put a physical model that maybe captures the physics of your system. So think of your thermodynamics or your kinetics or whatever that is. And then you're gonna add a machine learning model that can be a neural network or could be a Gaussian process as you wish, right? And if you train this model, what you're doing is you are trying to find the best physical representation and also try to find the best explanation or the best capturing of the error of the physical predictions. So to some extent, the machine learning model is learning what the physics cannot learn, what they're restricted to do. This architecture is actually quite popular in weather forecasting. In weather forecasting, they have very sophisticated models to capture the state of the atmosphere, but they understand that there are certain aspects they cannot capture with the physics, so they augment this with some data-driven model to try to do this. So this is quite popular approach. A little bit more complicated approach is you are going to embed the machine learning model within the structure of your physical model. For example, in the context of that chemical process that I showed you before, imagine that you have your unit operations models that capture the physics, and maybe you have a surrogate model that is part of the reactor, right? So a surrogate model of the reactor. So in this respect, you're capturing that inside the structure of your physical model. This is a little bit more intrusive way of building these hybrid models. And what these models are doing is enforcing physics on the machine learning predictions. That's a way to kind of interpreting that. The other interesting architecture that actually chemical engineers have been very, very active in developing is what I call a composite structure, similar to this, but I call this an implicit composite structure. So the idea is the following, okay? And I'm gonna go slow because this one is quite interesting. So imagine that you wanna build a neural network model that predicts how the output flow of a unit operation responds as a function of an input flow, right? A standard neural net architecture. However, you want to ensure that those input and outputs satisfy some basic rules. For example, you might say that input and the output have to satisfy mass balances, right? So that constrains the space over which the neural network is being trained, and that helps a lot to provide context to a neural network and to generalize the predictions, right? So the inputs and the outputs are not independent, but they actually have to satisfy these things, right? So to some regard, what you're doing here is build a neural network model, and you're going to enforce a set of constraints, for example, mass balances that need to be satisfied, right? A way to illustrate this or represent this in a visual manner is you're going to have your machine learning model making a prediction, but maybe this prediction violates the rules of physics, right? So what you're going to do is you're going to project it inside the physical region of interest, right? And this, again, very powerful approach to kind of enforce physics in your neural network models. All right, now let me give you some examples of why all of these concepts are relevant, right? So a few years ago, I started a collaboration with a experimental electrochemist, Professor Matt Gavey here in the department, and he's very interested in predicting properties of ionic liquids. So these ionic liquids have become very popular for a variety of applications. In this case, it was in the context of batteries. You can use them as electrolytes. Okay, there are very well-established physical models for predicting conductivity in these ionic liquids. So this goes back to Nernst and Einstein. So this is the standard thermodynamic model. And you see from this very simple physics model that you can actually predict conductivity primarily as a function of viscosity and also of the radius size, right, of the cation and the anion, right? So very simple model, and it does very well. So when you compare against experimental data, you see that you can capture very, very well the conductivity of many ionic liquids. However, you also see that there are several ionic liquids that deviate from this behavior. So this means that this model is not capable of capturing those features that go beyond what they call hydrodynamics. So it cannot capture effects that do not have to do with viscosity, particularly, right? So that means that you need to build more sophisticated models. So what we did was to say, okay, we're gonna take all the descriptors available in the literature. So we went to all the databases that exist for ionic liquids. We were able to collect over 100 descriptors of ionic liquids. And this goes from simple properties like conductivity, viscosity, density, to structural descriptors. What is the molecular structure, the geometrical features, the polarity of the molecule, to even more sophisticated structures like connectivity in the form of a graph and things like that. All of that information can be passed to our machine learning model. But what we did was to train a model that combines this Nernst-Einstein model, and we correct the predictions, particularly for those that the Nernst-Einstein model cannot predict, to try to make the best prediction possible, all right? So we build this physics-informed machine learning architecture. So these are the results. And the results were disappointing, but also very interesting. So what you find is that this is the best you can do with the Nernst-Einstein model. So we standardize the prediction error to 1, right? So this is the best you can do with just the pure physics model. Then what we do is we start augmenting with the machine learning model using different types of descriptors. So you see that this descriptor improves prediction, including this descriptor improves prediction. So that means that these features are very important. Viscosity, cation polar area, very important, right? But then you see that the machine learning model saturates and it cannot keep improving anymore, right? And even at some point, if you feed all the descriptors, you start finding out that the model starts overfitting, right? So the take-home message from this is the following. It doesn't matter that you have the most sophisticated neural network architecture if the input data that you feed does not capture the physical information of the system you're trying to predict. This is something that I feel in chemical engineering we don't put too much attention to. We always assume that, oh, the neural network, as long as it's deep enough and as long as it has a million parameters, it's going to be able to predict. And I say, no, wait a second. If you don't feed the right physical information, it's not going to work, right? It's just garbage in, garbage out, right? And that's something that kind of I'm trying to explain here. So this was a good discovery for us because that means that the information that people are publishing in ionic liquids is not sufficient to predict conductivity. That means that we need to be computing additional information to be able to build these models. And that was a good finding from our side. All right, I wanted to show you also another application where you encode physical information for molecules, right? And this was for an application of graph convolutional neural networks, okay? Graph convolutional neural networks are similar to neural networks, but the input, X, is not a vector, is actually a graph, okay? So what you do is you input a graph, and then what you're gonna be doing is analyzing how these different nodes in the graph are connected to one another, and you're gonna summarize that information into a simple vector, right? So how does the architecture looks like? Imagine that you input the molecular structure of a molecule, right? Encoded in the form of a graph. You're gonna conduct this sequence of convolution operations that are gonna try to analyze the connectivity of these nodes and also how information is connected in there. You're gonna activate that information and then you're gonna summarize it. And ultimately, what you do is summarize everything into what people call a feature vector, right? That feature vector, you can feed it into standard neural network architecture, right? So a graph convolutional neural network, all that it does is says, I'm going to start with a complex data representation. I'm going to extract the information into a feature vector. And once I have the feature vector, I can just feed it into a neural network, right? So it's a very simple approach, but very powerful, very, very powerful, okay? So now, this was an application where we wanted to predict properties for molecules, and we wanted to predict properties of vapor-liquid equilibrium, right? So we wanted particularly to predict activity coefficients. So my student Amy, my former student Amy Chin, she built a very large database, and I invite you to check it out because that's an amazing database that you can use for training your machine learning models. And then she was able to capture a broad spectrum of molecules, nitriles, aromatics, polar components, non-polar components, and then she was able to build binary mixtures, ternary mixtures, and so on, right? Then what she did was something really interesting. She said, you know what? I can represent these molecules as graphs, and I can build a graph neural network architecture, but what we found right away is that that information is not enough to predict the properties that we wanted. So what she said is the following. If you think about it, thermodynamic equilibria arises because of intermolecular interactions, particularly in the form of hydrogen bonds. So a molecule in a binary mixture interacts with another molecule in the binary mixture, and you want to encode that potential interaction, right? So what she did was to build a graph representation that not only captures the structure of the molecule, but also captures the potential interactions between the molecules. So I like to think about this as a hierarchical graph, right? Very powerful representation, and this was a big success. So we were able to find that this actually enhances predictions significantly. And it has a kind of big discovery for us. So you see that we can predict activity coefficients for binary and ternary mixtures, for polar interactions, polar, non-polar interactions, and so on. And we're able also to detect azeotropes and things like that. So several groups around the world in PSC have been kind of exploring this type of architectures, including the group of Alexander Mitzos, Arachen, also the group of André Bardot, and also Kaisenmacher in Germany and Switzerland. So this is a very interesting area. But again, the take-home message here is that it's not enough to just encode the molecules as graphs, but also try to think about how those molecules are interacting between themselves. That requires physical information, right? And that's why we're trying to encode this physical information. All right, very quickly, because I'm running out of time here. So let's talk about uncertainty quantification. Uncertainty quantification is very important, I think, because it's for two reasons. Of course, first of all, we want to predict if our outputs have high uncertainty or low uncertainty. But more importantly, this is important in the context of understanding how physical information can help you reduce uncertainty because it provides information precisely, right? More information is less uncertainty, right? So how do you quantify uncertainty of machine learning models? So if you have something like a Gaussian process, this is a very natural approach to capture uncertainty because the model is probabilistic by nature. So you're gonna get a mean model that is captured here, and you're also gonna get the uncertainty information in the form of its variance, right? So that's a very nice approach. The challenge appears when you have parametric models like neural networks, right? Because these neural networks do not have simple architectures, right? So they're complicated and sophisticated to optimize. So the standard approach to quantify uncertainty, once you learn the models, is you do maximum likelihood estimation, right? So you maximize the posterior of your model. You can add a prior if you want into this that gives you the optimal parameters. Once you have these optimal parameters, you can quantify or approximate the posterior distribution of your parameters, right? Typically, you do something like a Gaussian approximation of this. This is called in statistics a Laplace approximation, right? And once you have this representation, then you can compute samples, right? So you compute samples for your scenario, for your parameters, and then you propagate your those parameters through the model, and then the model gives you a kind of a variety of approximations. This is the most standard approach to quantify uncertainty. The problem is that it does not scale very well if you have models that have a lot of parameters, right? Like neural networks require a lot of parameters in general. So another very powerful approach that unfortunately I do not have too much time to discuss with you today, I can give you an entire seminar about this, is variational inference. This is an approach that I find really surprising at how effective it is. What you do is to say, I'm going to approximate the posterior of my parameters directly in the form of a model distribution that I have a simple structure for, and then I'm going to try to minimize the distance between these two distributions, this posterior and this posterior. And you can formulate that as an optimization problem. And then you can solve this problem using standard techniques of optimization. So you can use things like IP-opt, or you can use things like first order methods and things like that. Really powerful approach and very natural for capturing uncertainty. So I just wanted to make you aware of these tools because they're very, very interesting and very, very powerful, right? So yeah, the message here is that neural networks are a little bit more complicated, the calculations of UQ, but it's possible. It is possible to do. So what I'm going to do here is to show you why when we combine uncertainty quantification together with physics, you can get very interesting insights, right? This is the application I was telling you about before. So imagine that you want to learn the interactions of a microbial community, right? And you have access to data. So my former student, Jaron Thompson, what he did was to build 3 different models. The first model is completely based on physics. So this model is a mass and energy balance and basically says, these bacteria interact through resources. So they're trying to eat glucose, they're trying to eat each other, right? So they have interactions through sources, and you can express those balances very nicely. So those models are powerful, but they're incomplete, right? As you might expect. So what Jaron did was to incorporate a neural network to try to capture those aspects that we cannot understand. He said, you know what, this term over here is one that we don't understand very well, so I'm going to replace that with a neural network. And this term over here, also we do not understand very well, so I'm going to augment it with a neural network. And I want to show you in this kind of architecture that the way that we embedded the neural network was not obvious. It was not like we just added a neural network. It was more like the neural network multiplies this term. So Jaron had to do a lot of experiments here to try to figure out what was the right way of capturing that. He also built another architecture that was a little bit more lazy, like a lazy architecture, where it's like, I'm just gonna capture this architecture here, but then for the second one, I'm gonna ignore all physics and I'm just gonna directly capture this with a neural network. So to some extent, this is a little bit more flexible, but also does not encode too much information. And these are the results that he found, right? So these are the predictions with the physical model, right? And you see right away that you get a good fit, but look at the uncertainty predictions, right? There are certain scenarios that start blowing up and start doing things that these microbial communities cannot do. And this is the value of physical of uncertainty quantification, right? So uncertainty quantification will give you alternative scenarios for your parameters. And through those scenarios, you can figure out if this system is behaving in ways that you will expect or in ways that you might not expect, right? So you see here, yeah, pure physics does a good job, but it does not do the full job, right? So when you augment it with machine learning, this works better, and you see that you get very good confidence bounds for your predictions. So this is very nice. But you see that in this machine learning model, you see that the model in some scenarios crosses the negative, right? So the concentration of sulfide goes negative. And we know that from physics that concentrations cannot be negative, right? So that again tells you that there's something in this architecture that is not working out very well, right? The pure machine learning model is very good at feeding the data, but you see that it feeds the data in a way that is not physically realizable. This community cannot just grow exponentially like that. It just cannot happen, right? From pure physical information. So again, machine learning models, when you don't constrain them with this physical information, it starts doing weird stuff, right? So you need to be very careful with that. The best model that we were able to find was this second one, that is precisely this one that I was telling you here. You see that this one is consistent, the predictions make sense, and it do not cross the constraints of negativity. So that was nice to see. I'm gonna conclude the seminar by giving you some examples on how do we incorporate physics information in Bayesian optimization. So I'm gonna try to go a little bit fast, just in the interest of time. I don't wanna keep you here forever. But yeah, let me just conclude the seminar with this. For those that are not familiar with Bayesian optimization, very powerful approach to try to optimize systems that you treat as a black box, right? So imagine that you have a system like an experiment or a chemical plant, and you don't know any physics about this thing. You just know that if I give you an input, I'm gonna get an output. So I collect the data, I build a database, and based on the database, I build a machine learning model. For example, a Gaussian process model, but you can also use other models, right? So imagine now that I have my machine learning model, and I have the ability to predict not only the mean behavior, but also the uncertainty of my predictions, right? And then what I'm gonna do is I'm gonna feed this into something that I call an oracle. This oracle is gonna combine the prediction and the uncertainty to try to give you a recommendation about what is the next experiment that you need to conduct here. And this combination is very important because typically when you have few data points, right? The model will tell you go somewhere, but then you don't trust the model very well yet, right? So for example, here I'm showing you, the model is telling you go here, but you say, you know what, here I still have a lot of uncertainty, right? So maybe I still do not want to go there, right? So maybe let me explore other regions to try to gain information and reduce my uncertainty, right? So Bayesian optimization try to kind of does this trade-off. It's kind of gonna send you to certain locations to try to gain information. Once you have good enough information, you go to other locations to try to optimize. And it's a very powerful way of balancing these two things, right? If you're interested in learning about Bayesian optimization, my colleague Joel Paulson is the absolute expert in this field. He has this very nice paper with Calvin Say from Imperial College, where they walk you through all of these different variants of Bayesian optimization. It's a really nice review that I invite you to check. All right, but again, I told you that the standard BO is just based on input-output data, right? However, you can also incorporate prior knowledge, right? So for example, this prior knowledge can be in the form of a physical model, or maybe it's a low-resolution model that I'm gonna show you in a second how that might look like, right? So the idea here is that I'm gonna decompose my performance measure in terms of my physical model or my reference model and a residual model. This is what we do not know about the system, right? So I basically approximate this with this plus this. And then what BO is gonna do is that instead of learning, G is gonna learn the residual. So it's basically gonna learn to correct the physical model in some clever way to try to accelerate the optimization, right? So this is nice because typically you can learn residuals much better and typically focuses the search on some specific region. So for example, here I'm showing you that the contour plots of f of x, right, cannot be perfectly captured with the physical model, but it captures it well enough to at least tells you that you should be going in that direction. And that is very valuable information to try to narrow down the search, right? For those that are familiar with model predictive control, particularly internal model control, this looks exactly like internal model control, right? This goes back to Manfred Morari in the 80s, right? So the idea is that I have a system from which I collect data, and then I have a reference model, right? And then I combine these two features to try to build some database, and then I build my model to go back, right? So it's very, very analogous to that. So what we did in this application was we're gonna tune the parameters of a model predictive controller. We're gonna use Bayesian optimization to tune those. We're gonna have a reference model that captures a low resolution model predictive controller. So I want you to think of an MPC controller that I can optimize very, very quickly. So maybe have a very short horizon, right? And I'm gonna use that as my reference. And then I'm gonna have a high resolution model predictive controller as being my actual system. And so what I wanna do is exploit information of the low resolution MPC controller to optimize the high resolution MPC controller. So this is one way of gathering information. And this is how the results look like. If you try to directly optimize these parameters of the controller without any prior information, just based on observations of the MPC controller, you see that the BO is searching everywhere, and eventually converges, right, to the region of interest, but it has to do a lot of simulations. And remember that I told you that each one of these simulations takes close to 3 hours, right? So this takes a long time to discover, like a long, long time to discover, right? When I incorporate this low resolution MPC controller, that low resolution model is good enough to actually tell you, you know what, the optimum seems to be close to this region. So I want you to focus on that region, and that drastically reduces the computational time. So it helps me kind of narrow down the number of simulations that I have to do. All right. This is another really powerful way that you can use physics information. A physical model is trying to capture what regions of the design space are the most promising ones, right? Like the ones that have minimum cost or maximum performance or things like that, right? So you can use the contour plots of this physical model, let's say your thermodynamic model or whatever that is, to identify those regions, right? And then what you're gonna do is you're gonna build a BO architecture to try to search in these regions in parallel, right? So this is a very clever way of partitioning the space in a way that preserves physical information and narrows down the search. So that's what I did with one of my former students, right? So we partition the space using these different physical models, and then we train a BO model in these different regions, and then we do parallel computing to try to do this. This allows you to do high throughput experiments, right? So if you have a parallel cluster, or you have multiple reactors or whatever that is, you can search in these different regions independently, right? So this is how the partitioning looks like for a simple example, right? So you see, this is the performance profile of the real physical model, and this is the one obtained from physics, right? So according to physics, it tells you that this region is the optimal, and we know that clearly that's not the case, right? But you see that it follows more or less the shapes of those regions, right? And that's what you want in these physical models. All right, and this is how the solution of these different approaches looks like. So if you just use a standard BO, you see that you have a lot of simulations that you need to do, right? If you partition the space using these level sets that I was showing you, you converge very, very quickly, right? So you can actually explore these multiple regions simultaneously, and you kind of get to the optimum much, much faster using these parallel optimization approaches. All right, I believe this is the last example I wanted to show you. I hope that is indeed the case. Let me just monitor. So another way to exploit physics is to say, you know what? I know the space. Based on my physical model, I can tell you based on these level sets what regions are important or not, right? And then through those, you can constrain, right? As opposed to prioritize different regions, you can also constrain and says, you know what? I'm just gonna eliminate those regions of the space that are not promising. I'm not even gonna search through those, right? So for example, you say, according to a physical model, this region is not promising, so I'm just gonna cut it down from my search space, right? So this helps you kind of prioritize certain regions that you might wanna look for and just throw away all those regions. This becomes very important when you have these very large design spaces, because you're not gonna be able to search over all the design space. You have to cut it down somehow, right? This is exactly what we did in this application of the solvent selection. We use CosmoRS, which is a thermodynamic model, to try to predict what solvents might be reasonable or not. And we cut down the space, right? We just cut down the space of what is not thermodynamically possible, and then we narrow down the search. And this is real experimental data. You see that very quickly the BO is able to identify those solvents that behave the best. But again, it's very important to use this CosmoRS engine to try to narrow down the space and search efficiently, right? All right. The last thing I wanted to tell you today is this combination of physical and latent spaces. I find this very fascinating. And in my mind, as a chemical engineer, to this day, I still don't understand this very well, and I eventually want to understand it well, okay? So let's talk about this. A few years ago, there was a group at Harvard, Rafael Gomez Bombarelli, which is now at MIT, and Alan Aspurubusik is a Mexican scientist, is at Toronto now, where they say, you know what? These molecular structures are complicated objects that are discrete in nature, right? So a molecule is a discrete object, right? So as a result of that, if you're trying to optimize for molecular structure, you need to solve a mixed integer program. So that's complicated, right? So what we're gonna do is we're gonna project that into a low dimensional space that is continuous using these autoencoder networks. And then we're gonna search for the best molecules in that space. And that for me was a big boom. I was like, oh my God, how come I never thought about this, right? So the latent space is physical, is much easier to search for, however, does not have physical interpretation, right? So this is an abstract space, but it's very easy to search for. And that's what I find very interesting about this. Sometimes physical spaces, we say they are great, but they're not the best ones to optimize for. So maybe another alternative space might be more useful. Also, another thing that a lot of physicists do, they like to reduce data. And I find this very interesting because they use their physical understanding to try to reduce a complicated object like a molecular simulation into a simple descriptor. For example, they use a lot of descriptor that is called the radial distribution function. The radial distribution function is a summary of where the molecules are located in space. So this is one way of using physical information to try to reduce your data. However, it's not possible always to go back to the original space from this. You lose a lot of information in here. So that's why I find this topic really, really interesting, because I like to think that physics has many benefits, but also has drawbacks. And I feel that sometimes we say, oh, physics is always the best, right? It's like, yes, for some things, but maybe operating in some physical spaces maybe is not great, right? Maybe looking into these machine learning architectures might be beneficial. And maybe let's just combine it in a way that is good for both worlds, right? So just to give you an example of how this, how you can use these things. So we did this very interesting study with Professor Arturo Jimenez in Mexico and his student, where we say we're going to optimize the topology of a complicated distillation system. So the discrete variables that affect this design is what is the type of solvent you want to use, what is the feed stage, those are discrete variables, and what is the total number of stages, right? And in addition to that, you have continuous variables. Then what we did is we take that discrete space and we project it to a continuous space using an autoencoder, and then we search for the optimal design in that space. And that's directly analogous to what people do for the molecules. And what we found is that we can very quickly find the Pareto frontier of the system, right? So again, projecting these original discrete physical spaces into these abstract spaces might be beneficial for computational reasons. To this day, I still don't understand why this approach works very well. And I still do not understand under what conditions you can represent a discrete space as a continuous space. But if you think about it, this is exactly what large language models are doing. We're looking from a discrete space in the space of words and sentences, and we project that into continuous spaces, feature vectors, right? And then we search for structures of language in that space. So that's what I find very, very interesting about all of these things, right? So with that, I'm going to stop, and we'll leave you some time for questions, but thank you for your attention. Thank you for the invitation, and I hope that you learned something useful. And so I'll take it from here. Thank you for your attention.
Vitor,
Yes.
thank you very much. And your presentation was very interesting because we are now very concerned about inserting physical knowledge in our models, and you showed
Yes.
different ways of doing that. So I think the
Yep.
audience has questions, and I will ask them to please use the chat so that I know who is going to talk first, and then I will pass the word for each of the ones that put the names in the chat, please. Okay. Um, well, I'm not quite sure if it is okay. Yes. Hi. Did I have some difficulty here using the internet? Can you hear me, please?
Yeah,
Yes.
I can hear you.
Because it kind of froze here to me. Okay. I think if there is someone that wants to start, because no one has yet raised the hand or put a message in the chat.
I think Jimiro has a question.
Ajimiru. Okay, so please, Ajimiru.
Okay, thanks, Mauricio. And thanks, Victor, for this very nice talk about this physical knowledge and machine learning modeling, this hybrid modeling. My question for you is, you show us today the very broad ways to do this combination of physical knowledge and
Yes.
machine learning. Yes, I think you have to explore all of these and many more.
Yep.
But you have some insights in how to direct the modeler, the people that will build the model, how to choose the best combination of all these possibilities. Because
Yes.
instead of doing just an this problem, I will choose this kind of combination. For that problem, I will do that one. You have some insights on that?
Yeah. Yeah, exactly. I think modeling is an art, and it will remind an art forever, I think. I think that similar to how we have been doing modeling even before this emergence of all these neural networks and machine learning, that was still an art, right? Is you need to use physical understanding of your system first, in my opinion. Try to exploit the physical understanding as much as you can, because that's more generalizable, is more more structure, more first principles. And then if there are certain aspects that you don't understand, that's when you can start using some of these tools of machine learning, right? I think what we're seeing right now with all of this emerging of tools is that they give us additional tools to be able to make the model discrimination exercise easier. For example, these tools of uncertainty quantification are very useful, because it's not enough just to build these models, but also make sure that this uncertainty representation of your predictions makes physical sense. It's not just that the model makes physical sense, but also that uncertainty makes physical sense, right? So I think that there are additional tools that you can use, and also standard tools of statistics, right? Like a K-CAPE criterion and things like that, so that you can measure how good your model is, and also how interpretable the model is, right? So I recommend just using some of these modern tools of cross-validation, modern tools of uncertainty quantification to augment that. But in my opinion, this art of modeling is not gonna go away. We just have more tools available for doing that selection, but we still need to be able to rely on our physical knowledge. It's gonna be very difficult to automate that, in my opinion. And I have seen in many of these applications I was showing you, it was very difficult to understand what is the right amount of physics. That's another thing that I tell my students. It's not clear what is the right amount of physics. Is mass balances enough? Or you need to add mass and energy balances, or you need to mass and energy and thermodynamics, and at that point, it's already a physical model, right? So it's not right, obvious what amount is possible. Right? But yeah, maybe high-level question and high-level answer, but yeah.
All right, thanks, Victor. I'll let the students to do the rest.
Yes, it's very nice to see that many students are enlisted here to make questions. So now, Leonardo, please.
Hi, Victor. Nice presentation. I appreciate your time to do this seminar for us. And I want to go one step back right now, because we talked a lot of our opportunities to do this hybrid approach or interpretable approach. But I want to talk about feature engineering, because sometimes, as you said, we just think, okay, if I put these features into these neural nets, it's going to be the predict with high level of accuracy. But sometimes it's not like that. And you have some tips, some advices to do this feature engineering, because as you said, for example, in the example, that you realized that the model in the literature was not enough. The profits were not enough to predict. So do you have like a tip for this kind of feature engineering?
Yes, very good. It's very similar to what Argemiro was asking, that feature engineering is a modeling exercise, right? I always tell the students, we talk a lot about data representations. Well, selecting the right data representation is a modeling choice. So it's part of your modeling exercise, right? So you get into the same types of questions that they're a little bit different in one important regard. Some of this information, some of these features are more difficult to obtain than others. For example, I can get SMILE strings for free. Basically, those, as long as you have the molecular structure, you can get it from a repository, no problem, for thousands and thousands of molecules, right? So those features are very inexpensive to obtain, right? However, there are some features that are highly informative, like this sigma profile, but take a long time to compute. So a single sigma profile might take you 30 minutes to compute, right? So as a result, you have a lot more information, but it's more expensive. So I would say that it's very important for the modeler to understand that trade-off between information and accessibility, right? So typically the most accessible features are not the most informative. And it's important to kind of quantify all of that. And it's important also just to try multiple representations. Do not just go with one. I think it's important to try multiple, to try to see if all these features have complementary sources of information, or if one feature implies the other, right? So I also recommend that people try that out, right? And also my general recommendation is always try to use physics whenever possible, right? Because I talk to companies like Dow Chemical, and they tell me, look, for us, we can build a model, and maybe the model works very well to predict, but then we need to verify if something bad happens with this molecule. So maybe it's toxic or explosive, and we didn't know. Someone is going to come to us and ask, how do you make that prediction? And if we don't have a good answer, there's a lawsuit in there, right? So the government will get upset. So I think interpretability, I think is, in my opinion, the most important aspect of all of this, right? Is we need to go back into what were the key features and what information might not be capturing those features and what might be capturing those features. So long answer, but again, this is a modeling exercise. It's part of an art.
Because in your previous work, I realized that, for example, I was trying to use a model from yields.
Yes.
But when I changed the base to mass, for example, I discovered that it was much better to the prediction, because I kind of strengthened the correlations between the variables. So the model was better, much better than before. So it was kind of an important thing to use for the predictions, because before it was not possible to do the prediction.
Excellent, very cool. That's great. And then the other maybe advice that I give you is try to use these autoencoder networks, or maybe something simple like PCA. PCA is an autoencoder network, but it's linear, right? To project all your input data into a low-dimensional space. And that is very useful because that helps you identify if there's a lot of redundancy in your data. So maybe you have many features. So maybe you have like thousands of these kind of properties, but maybe only 10 are really important. So PCA will tell you that that latent space is of dimension 10, right? And that's important to know, right? I don't need those 1,000 features, maybe just 10 is enough. And that's also important to know.
Right.
Great question.
Yeah. Thank you, Gabriela. Now, Gabriela.
Hello, thank you for the presentation. It was very interesting. I have a question. What are the research lines your group is pursuing in this biological area? Because I found the article you show was very informative. It's different.
In the biological space?
Yes.
Yeah, excellent. Yeah, I have a couple of projects that involve this physics-based machine learning. This one is one of them where we're trying to understand these interactions of microbial communities, right? Or more general, you can think about it like, if you want to model a fermentation system, right? So we know certain physical aspects, like we know the monod kinetics and things like that, but maybe there's certain aspects like mixing that might be difficult to capture, right? So maybe how do you combine these physics together with the machine learning model to do that? And another one that I did not show you, but I kind of briefly mention is this one. We also work a lot with bioengineers to try to design bioprocesses to conduct different functions. So this process that I'm showing you here, what it's trying to do is process wastewater from dairy farms. So in Brazil, for example, in Brazil, you guys have a lot of meat farms, right? A lot of cows for meat. So in Wisconsin, we have a lot of cows for milk. And this wastewater contains a lot of nutrients. It contains a lot of phosphorus and a lot of nitrogen. So what you want is to capture those nutrients using cyanobacteria. So we also kind of engineer the cyanobacteria to capture that, right? Because if you don't capture those nutrients go into your rivers, right? So maybe they go into the Amazon River, and then they end up in the Gulf of Mexico or weird places, right? So you might end up in the Atlantic Ocean or whatnot. So you need to be careful with that, right? So maybe that's another example of kind of applications we're looking at. And I think that machine learning is particularly good in bioengineering because in bioengineering, there are a lot of things we don't understand. These microorganisms are really complex. They're very complicated. So I think that's where machine learning model really helps you.
Okay,
I remember
thanks.
one paper by Psychologius and Unger. I don't know if you remember in the 90s, and it was already developing hybrid models for biological systems.
Yes.
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 In the list now we have João Neto.
Hello, Professor.
Hi
Thank you so much for the presentation. It was very informative. Really, really good overview of the whole context of physics-informed neural networks. And my question is a bit more directed to a specific part of the implementation. I've been reading some papers about hard constrained implementations of pins. And from what I've seen in the literature, there is a tendency to use basically polynomial solutions to implement those constraints, multiplying the output of the actual model. Yes. But I've also read that a big problem right now is that kind of warps the way that the model tries to understand the patterns, learn the patterns in the data, and depending on the type of function you put multiplying that can change completely the behavior. So I'd like to know if you had contact with it and if you have any specific approaches to actually choose the type of function to actually use on the multiplicative term specifically.
Yes, very good. Excellent question. I recommend that you look at this review paper that we wrote with my postdoc Angan. So where we visit different approaches for doing this. So there are a lot of references there. But yeah, if I could summarize, the answer is the following. There's architectures, for example, something that Chan Lee and Professor Farouk Hassan have been doing, where it's a really clever approach. It's like you do a neural network and then you project using some of these projection constraints. So if the projection is linear, it's simple. It's a simple matrix multiplication, right? So that's not a big issue. However, Professor Hassan also says, well, what happens if that model is nonlinear, right? So in that case, what they do is they solve an additional optimization problem that projects the output into the physical region. Well, that projection is not obvious how to achieve because projection operations are ill-defined. For example, a projection operation could be take this point to the closest point inside the feasible region. That makes sense. But why do you want the closest point? Why not this point in the interior, right? In the center, for example. So it's a little bit tricky to select what is the right projection to do there, right? Another approach is to what I would call the Larry Bigler approach, which is my advisor, where you will call it a simultaneous approach, where it's like, let's learn the neural network and the physical model together. Do not do the neural network first and then the projection. Let's do it together all at once. So that means that you solve an optimization problem, right? Like what I had maybe here. So you solve an optimization problem, right? Where you are embedding all those physical constraints directly into the optimization problem. What are the benefits of that? The benefits of that is you don't require projections. So that is implicitly part of the learning process. The caveat is that is a more complicated optimization problem, right? But nowadays you have very powerful solvers that can do that, right? So I will say that it's possible to do. So I recommend that you check that paper that I told you, because we cannot go into the details of why that simultaneous approach maybe is better than the sequential projection approach, and in what cases might be beneficial or not.
Perfect. Thank you very much.
Yeah, very good.
Thank you. I think Gustavo has written a question here.
Está com o microfone fechado, Maurício. Your micro is closed.
Yes, because Gustavo sent a question. I think he isn't with a mic available now. So I will read his question. He says that in case of modeling and identification with machine learning combining with differential equations, he asks how to ensure closure of the model in terms of states. For example, in your ecological nodes, how did you choose your features to serve as states to identify your dynamics? That's Gustavo Calva's question. Yes.
Yeah, that's a great question that in this context, in this application, we did not think much about, because in this application, we were assuming that all the variables, which are my substrates and my metabolites, I can measure. So basically all the states are measurable, right? If you have a situation in which you have observables, but then you have a hidden state, right? They are neural network architectures, like recurrent neural networks, that allow you to introduce those latent variables. So you can artificially introduce those latent variables, and then you just try to learn what is the mapping between the latent variables to the observable variables, right? But yeah, it's difficult to select what is the right latent variable space in general. It's very, very difficult to select. But yeah, that's the only approach at this point that maybe I can offer.
I don't know if there are any more questions, because I'd like to ask you something. If
Yeah.
I don't know if Ajimiro has another question. I would have just a last question. Okay, so Vitor, I'd like to know your opinion also as the educator you are. For example, both for undergraduate and graduate students, I think
Yes.
we know for sure that we have to they have to learn the fundamentals, the thermodynamics and the transport phenomena and the kinetics, etc. But do you think now that with all the development of the machine learning techniques and mostly the availability of data, so data-based approaches for modeling are important for different applications in the chemical engineering field? So do you think, I don't know how it is the scenario in the American universities, but do you think we should also include these approaches for, let's say, hybrid models in the formation formation of the future chemical engineers?
Yes. Yeah. There are many ways that I can answer that question. But the first one that comes to mind is the following. The number one thing is that you absolutely need the fundamentals.
Yes, sure.
You become valuable to a company for the fundamental understanding that you have. I talk about this over and over again with the chemical companies. They say, look, I can hire a statistician to build the most sophisticated machine learning model, but if they don't understand what is the actual application, it's not useful, right? So you definitely need to continue to enforce those physical knowledge. But yeah, definitely nowadays, chemical engineers need to have some basic working knowledge of what is the spectrum of techniques that are available to them, right? what is a hybrid, at least to know the terminology, right? What is the hybrid modeling? What type of approaches you can follow for that hybrid modeling? Why it's important to capture physics and why it might be limited, right? How do I analyze data based on these machine learning models? What type of data representations exist, for example, for molecules? So things like that, so they know that there are different ways of encoding that information. So yeah, so I think definitely chemical engineers need to be exposed to some of that basics. Now, chemical engineers are very well trained, I think, in terms of mathematics and physics, right? So they are very, very well trained. So I think for them, it's not such a big jump to go into machine learning. It's an application of calculus, statistics, and optimization, right? So I don't see that being a big drawback for them, right? I think they can do it. They can do it. And I see it with my students all the time. I have undergrad that started in the PhD here at Wisconsin, and they say, I have no experience with machine learning. And they say, I don't care. Don't worry about it, right? And within 6 months, they're already masters in autoencoders and things like that because they have mathematical basis to do it, right? So yeah, so I wouldn't worry too much about them getting into it. I don't think it's a big deal.
Okay. Oh, thank you. That's what I always say to my control undergraduate students, that you can only control something that you know about it.
Yes.
You have to know, you have to understand it in order to proper control it. And so I think that a big message that you brought here is that the expertise, our knowledge, is fundamental also for these applications too. And so I thank you very much. I don't know if Ajimiro has another question so that we can come to the end of
Yeah, just a thought question. Will be the LLM a good artist in terms of modeling?
Yeah. Yeah, I think that the LLMs can help you a lot to navigate quickly what different modeling structures you might be able to explore, right? So it can, cloud, if you add cloud code, right? Give me a physical model that combines thermodynamics with that, it will give you different architectures and it will try it out, right? But then our role in that case will be just to diagnose and to kind of troubleshoot issues that might encounter the LLM. But definitely the LLM, I always think of LLMs like a very powerful search engine that allows you to search for and try many different things all at once. So definitely LLMs, I think, are going to help a lot. I have some other thoughts about LLM, but I think maybe it gets a little bit philosophical and abstract. But maybe I'm just going to say it. I think the other thing with LLMs that I find fascinating is that they're starting to show that if you think about it, we use mathematics as an intermediary language to try to do engineering, right? So mathematics is the language we have chosen to make decisions and to inform our decisions. But LLMs are showing that potentially you don't need mathematics at all, right? So maybe you can just go straight from data to learn this latent space that you can call mathematics or you can call something else to make those decisions, right? But again, the powerful thing about mathematics is that it allows us to understand. It allows us to learn in a structured manner, right? So, but yeah, this is another philosophical aspect that maybe I'm constantly thinking about.
Thanks, Victor. Good thought for the weekend.
Thank you.
Thank you. You said that it's a bit philosophical right now, but you said that you were very proud of contributions from chemical engineers for this area. Do you think that in general, artificial intelligence could learn these facts that we use constraints in our problems in order to use artificial intelligence for general applications? Because of problems, yes, that would be a lesson that we could be showing how we work for general applications.
Yeah, if you think about it, the success of PSE over the last 40 years that has been around or more is that we have tackled problems of the chemical industry. So you look at the work of Ignacio Grossman, right? Trying to optimize heat exchanger networks, trying to optimize these highly nonlinear processes. If you look at the work of Bigler as well, like trying to optimize those chemical processes. Chemical processes are really difficult problems, right? And that has driven a lot of inspiration for methods that other communities are not aware of, right? So I think that if we continue to push for chemical engineering applications like molecular design and optimizing these mixture spaces and things like that, we're gonna find the need for methods that can be potentially be applied to other domains, like similar to the work of Ignacio and Larry that have been applied to everything, right? Because applied to airlines and things like that. Because chemical process, I feel, is a very challenging application that bridges a lot of different expertise. So yeah, definitely, I think we can contribute a lot as a PSC community, but we should target challenging chemical engineering applications, right? Don't start working on quadcopters and things like that. I mean, if you want to work on that, great. But I think chemical process is really where we should be focusing our attention.
Yes. Okay, Vitor, thank you very much. We are very thankful for you for giving this presentation for us, and I hope we can keep in touch, our group and you and your group, because the lines of research that you are pursuing are very, in a way, are connected with things that we are doing, and also very inspiring. So thank you very much.
Thank you. Whatever you guys need, happy to work with you. Happy to also go visit you in Brazil. It's one of my favorite countries in the world.
Yeah.
So, obrigado, and have a good weekend.
Muito obrigado, muito obrigado. Thank you.
See you later.
Bye bye. Thank
Bye
you.
bye, guys. Thank you.
Thank you. Take care, everyone. See you soon.
See you.
Tchau, pessoal. Até a próxima. Eu vou disponibilizar, tá, essa gravação aqui, tá? Muito obrigado. Vou encerrar aqui a gravação e a chamada.